Hello, Chem Kids. We are back with another edition of kinetic rate laws. So today I'm going to explain where the half-life equations come from. And no, do not flip out, Brooklyn. Listen to me, I'm not going to expect you to be able to derive these equations. I'm just showing you where they come from and the significance of them. So that way they just don't appear like out of thin air. So we're going to go through all three. So let's start with, you have a zero order. Now here's the whole idea of what a half-life is, okay? So a half-life is the time required for a concentration to become half of what it was at the beginning. So let's say that your initial concentration was, I don't know, 0.25. So what the half-life is going to give you is how long it's going to take for that concentration to become half of that, hence the term half-life. Some reactions have extremely short half-lives. Some reactions have very, very long half-lives. So that's what they use in like radiocarbon dating, like radioactive carbon-13 has a very, very long half-life. So any living organism has a certain amount of carbon-13 in it. So if you know how much, when that decomposes, it turns into carbon-12. So like if you know how much carbon-13 there is in the beginning, and then you know how much carbon-12 there is when you take that sample, then you know how long it was when that tree was alive, or that whatever that organism was alive, because obviously once that organism dies, then they're no longer uptaking any more carbon-13. So it's a handy way to figure out the age of certain substances. So if you can figure out the process on one of them, it works the same way. So let's say you have a zero order reaction. So you have the concentration of A is going to equal negative KT plus the initial concentration of A naught. So here's the short version. We go, okay, well, we want this to become half of this. So we're going to let that be 1/2 A naught is going to equal negative KT plus A naught. Oh, okay, seems reasonable. So if we do a little subtraction and we subtract this over, okay, we get negative 1/2 A naught is going to equal negative KT. And then to solve for time, then we're going to divide this over, and we're going to get this half-life then is going to equal A naught divided by 2K. Now, oddly enough, and for those of you that have been my students, which is all of you at this point, you know that the units have to work out. Okay, well, that initial concentration up there is going to be in molarity. So if you remember from the fact that K in the zero order has to have units of molarity per second, so then the molarities cancel out, the seconds flip up, you get seconds, voila, there you go. So here's what's important, is that if it's a zero order, and again, zero order reactions are very rare. If it's a zero order reaction, then your value of your half-life is dependent upon two things: the initial concentration and the value of K. So if you have a higher concentration, you're going to have a longer half-life. If your K value is larger, hey, your half-life is going to become small. So this is just the process. Zero order reactions are the most rare, probably not going to see that. But now let's talk about first order reactions. Now the math here gets a little bit weird. So if it's a zero order, you have the natural log of, I'm going to go ahead and put that as A naught, is going to equal negative KT, I'll put a little half-life there to indicate that we're talking about half-life, plus the natural log of A naught. So we're going to make this simple. So we're going to let the initial concentration of A be 1, okay? We could let it be anything. We could let it be 10, we could let it be 20. I'm just going to let it be 1 because the natural log of 1, wait for it, you can plug this into your calculator if you don't believe me. Isabel, I'm sure you might do this, but if you take the natural log of 1, you get 0. So then, if I come in here and do that, then I've got the natural log of 0.5, okay? And oddly enough, So if I let the initial concentration be 1, then at my half-life, that becomes 0.5. Okay, that's kind of clever. And then I've got negative kT times 1/2. So this whole thing here goes away. So what I'm left with then to solve for this, so I have the natural log of 0.5 divided by a negative k is going to equal my half-life. Okay, all right. Now, this is where the magic happens. So if I take the negative natural log of 0.5 divided by k, so the negative log of 0.5 is 0.693. That was horrible. Let me write that again. So the half-life is 0.693 divided by k. So on your sheet, this is where that 0.693 comes from, okay? Because of the fact that's the natural log of 0.5. Now, here's what's going to be important. With this one, and you'll see that this is the only one that this is true, this is the only one that the half-life isn't dependent upon the initial concentration of A. So if you come up here to that zero order, oh, you have to have the initial concentration. The half-life of a first order reaction isn't. It's only dependent upon that value of K. Now again, this is where you have to look at the units. Well, if you remember, the units of K for a zero order are just 1/seconds. So the seconds flip up, you get units of time that's a half-life, boom, you're off to the races. So if something has, with this one, your half-life is only dependent upon the value of K. So if your K value is really small, your half-life is bigger. If your K value is large, your half-life will be smaller. Okay, so we got that one. Now for the second order reactions, we're going to do that same process again. And so this one we're going to have 1/A is going to equal KT plus 1/A0. So if we come in here and we go, okay, we'll rewrite this a little bit. We're going to make this 1/2 times, oh, that was ugly, A0 equals KT plus 1/A0. Now, if you're playing along in the studio audience and you want to do a little bit of math, then you can sit here and go, oh, that 2 is going to flip up. So I have 2/A0 equals KT plus 1/A0. And I subtract this over, I divide by T, I get my half-life equaling 1/K times A0. Now, with this one, okay, again, look at what happens with the units. So because of the way that this concentration is in molarity, and this is, my K is 1/molarity seconds, my molarities cancel out, my seconds flip up, okay, the units work out. So this is where you have to view this as being kind of like a holistic thing with the units. So the units on all three of these, whether it's zero order, first order, second order, always have to produce units of seconds or hours or days or years or whatever that may be. So here's what's important. Notice with this one, this is also dependent upon the initial concentration of A0. So this is what makes first order reactions so unique, because they are the only ones that aren't dependent upon the initial concentration. So how you use this, okay? So let's say that, let's work with the second order reaction here. So let's say that the K is 0.10 m to the -1, s to the -1. And the initial concentration of A is 0.5 molar. And we want to figure out the half-life. Oh, okay. So my half-life would be 1/0.10 m to the -1, s to the -1 times 0.5 molar. The molars cancel out. The seconds flip up. I get a half-life then of 20 seconds. Now, if we change this, though, and we make, instead of the initial concentration being 0.5, let's say we say, well, Mr. Burkamp, what would happen if we changed that thing up a little bit? Okay. Well, let's say my initial concentration becomes 0.250. Okay. So the only thing that's going to change is this is going to become 0.25. Now, if you do the math, then you get a half-life of 40 seconds because of the fact that you're dividing by a smaller number. So as my concentrations of A become smaller, my half-life becomes a bigger and bigger number. All right. So how you can use this. So let's say that we have a first order reaction. Okay, this is going to be important. It's a first order reaction. And the half-life is going to be 40 minutes. Okay, so whatever concentration I have, it's going to take 40 minutes for that concentration to become half of that. So I want to do a couple of things. I want to calculate the rate constant. And then I also want to determine how long it's going to take for 75% of the reaction to be completed. Okay? So, the first part's going to be pretty easy. My half-life is going to be 0.693 divided by K. So then I know what my half-life is because of the fact that we said my half-life was 40 minutes. So I've got that number. So the only thing I don't know is K. So if we do a little bit of algebra here, stay with me here. So that's going to be 0.693 divided by my half-life of 20 minutes. So I get 3.47 times 10 to the minus seconds over minutes. You could also write that as minutes to the negative 1. Now, if you're really hardcore and you want to do this in seconds, you can. I don't recommend it. It's the same math. You're just going to get a much smaller value for K. And since they already gave you this value in minutes, just roll with it. It doesn't have to be in seconds. But if you're really hardcore and going, oh, Mr. Burkamp, I just live for seconds. Okay, we'll change it into seconds. I'm going to leave it like this. Now, here's what we got. So since this is a first order, we know we're going to be dealing with natural logs of A is going to equal KT plus the natural log of A naught. Now, this is where you have to be careful, okay? So the whole key to this problem is that 75% of the reaction is complete. What that means is that this is going to be 25%. Don't put in 75% here because this is the amount that is remaining. It is not the amount that has been used up. Okay, I say again, this is the amount that is remaining. So there's a couple of things you could do. You could put in the natural log of 1, like you could let this be 100 and you could let this be 25. If you like that, hey, fine, go with it. What I would recommend is that I'm going to just say, hey, I'm just going to let this be 1. Okay? I'm just going to let this be 1. Then I'm going to let this be 0.25. Okay? You could let this be 4 and you could let that be 1. I don't care. Okay? I just like letting I'm going to use the natural log of 1 because that's going to drop that thing out of the equation because the natural log of 1, as we established earlier, was 0. So now if I go through this, so I'm going to take the natural log of 0.25 and this has gone away. Then I'm going to divide by K. That's going to equal my half-life. Now, here's what's important, okay? Here's what's important. Because of the fact that this is a first-order reaction, this K value is going to be a negative number, okay? So this is actually a negative value because of that slope of that line. So I'm going to take the natural log of 0.25 and divide that by negative 3.47 times 10 to the minus seconds, minutes to the negative 1. So the minute's going to flip up, life is going to be good. I get a value of, oh, that was horrible, 40 minutes, okay? Now, here's the other way that you can think through this problem, okay? This is the full-blown math. Now, in this situation, this works out because I specifically chose 75%. But if you think about it, if you start with a concentration of 1, after 20 minutes, that concentration is going to be 0.5. After another 20 minutes, after another half-life, then that concentration is going to drop to 0.25. So we actually, in this situation, didn't have to do all the math if we had just thought through what is happening in terms of, oh, I'm going to go from 1 to 0.5, which is going to take 20 minutes. And that 0.5 is going to drop to 0.25. Okay, well, that makes sense then, too. You can only kind of think through that process logically when it's going to work out to be like, 50, 25, 12 and a half, something like that. Most of the time, it's not going to play out that nicely. So this is why you've got to be able to have that technique. So let's say that you have one that's a little bit more complicated, okay? So let's say that you have something that's a first-order reaction. I do the first order because the math gets a little bit hinkier, just because it's natural logs. And we know 40% is consumed in 380 seconds. So what I want to figure out is what's the value of K, and then I also want to figure out what the half-life is going to be, okay? So here's the whole key to this. If 40% is going to be consumed, that means 60% is going to remain. So I'm going to go to that natural log of A equals negative KT plus the natural log of A naught. So again, I'm going to make this simple. I'm going to let this have a value of 1 so that this drops out. I'm going to let this be 0.6 because that's how much is going to remain. I know the fact that this is going to take 380 seconds, so now I know my value of time. So the only thing I don't know is my value of K. So I'm going to take the natural log of 0.6. I'm going to divide that by 380 seconds. And because of this negative sign, this is going to be a negative value over here. The seconds, because of the fact that I'm looking for my value of K, because it's the first order, my units have to be 1 over seconds, which is this is going to work out because anytime you take the natural log of something, all the units go away. So I get a value of 1.34 times 10 to the negative third s to the negative 1. So that's a very, very small value of K. Now, to get my half-life, I'm going to take 0.693 and divide that by 1.34 times 10 to the negative third s to the negative 1. I'm going to get 517 seconds. Now, let's think about this answer, okay? My answer had to be bigger than 380 seconds. And I know it had to be bigger than 380 seconds because at 380 seconds, I had consumed 40% of it, which isn't quite half. So then to get the time when it's going to consume half of that, then I know that answer had to be bigger than 380 seconds. So if I did this math, okay, and I got an answer smaller than 380 seconds, hey, I know I did something wrong. If this became like a really huge number, I probably did something wrong too, because at 380, I'm about half. I got to figure it's not probably going to take a whole lot longer to get to where half of that thing has been consumed. So don't be afraid to step back and look at a problem and go, hey, does this thing make sense? Okay, now, here's the last big equation for now. And it's going to be the natural log of k. I'll explain all of this in just a second. Okay, so this is what's known as the Arrhenius equation. This is not on your equation sheet, but this is a wonderful, 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 wonderful equation. Now, let me explain what this E sub A is. This E sub A is what we call the activation energy. And that's in joules per mole. So what this tells you is basically if you want to look at a chemical reaction as being like a roller coaster, okay? So what the activation energy tells you is how high that initial rise is on a roller coaster. So some reactions have very small activation energies. Some reactions have quite large activation energies. So we're going to spend a lot more time talking about activation energy eventually because it's important in terms of rates of reactions. So what's going to happen here is that what we're searching for is this number. We can't quantify this number. It isn't like, oh, hey, let's get out the activation energy probe and we'll plug it into the LabQuest. We have to figure out what's going to happen graphically and then work backwards. Now, here's the other huge part about this equation. It doesn't look like it, but this is y equals mx plus b. As jacked up as this looks, this is nothing but a linear function of y equals mx plus b. So this is your natural log of k. This isn't temperature. This value of k is your rate constants. So what you do, and this is your temperature in Kelvin, so what you do is, and you'll see this in a lab, so what you do is you run a reaction at different temperatures, and you figure out what the K is at a certain temperature, then you run it at like a higher temperature or a lower temperature, and then you go from there. So here's what's going to be important. What you're going to graph on your y-axis is that you're going to graph the natural log of K. So what's going to happen, like on the assignment, you're going to be given a bunch of different values for K. You're also going to be given a corresponding value of temperature that's in Kelvin, okay? Now, this R is the ideal gas law constant, which has to be 8.314 joules per mole Kelvin. So what you're going to do is that you're going to draw a graph. And what you're going to do is that you're going to plot the natural log of K on your y-axis. So you're going to start up here at 0, and then like -1, -2, so on. Down here, this is going to be 1 over temperature in Kelvin. So these numbers here are going to be very, very small, like maybe like 10 to the -2nd, 10 to the -3rd, something like that. So these numbers are going to be very small. So what's going to happen is that you're going to draw a line of best fit, like this, and you're going to find that slope. So you're going to pick a couple points and you're going to find the slope. So here's what's going to be important. That slope, okay, which is going to have a negative number, is going to equal that E sub A over R. So what you're going to do to find this activation energy, you're going to multiply R times your slope. Now, this is where the magic happens. So this slope, because of the fact that it's going to be change in y over change in x, natural log has no units. X is the only thing that has any units, which is going to be 1 over temperature in Kelvin. So you're going to take your slope multiply that by R, kind of a pirate thing, and that's going to equal your activation energy. So your slope, okay, times R, which is joules per mole Kelvin. So your slope was 1 over Kelvin, so that flips up. So you got Kelvin, those drop out, you get joules per mole, boom, there's your activation energy. So what's going to be important here is that you choose the right value of R, because remember, you have two, one that's in atmosphere liters and one that's in joules per mole Kelvin. So you want this activation energy to be in joules, so therefore this value of R has to be in R, which is that joules per mole Kelvin. Okay, so a couple of words of advice as we're working through this process. That 2 problems assignment from yesterday's assignment is going to be due tomorrow, which is Friday. Do me a favor. When you scan that, when you can change like the subject line, okay? On your subject line, when you upload it, and by the way, make sure that you're using that batch option. When you're using that cam scanner app, use the batch option so that you're not sending me individual pictures. On the subject line of the email, okay, type your name, okay? So you're going to have like Bruce, okay? And then maybe something like what the assignment is so that I can keep track of it. So maybe you say Bruce graph assignment, okay? Something like that. So when you send me that PDF file, please do not leave it as just the number, because I'm going to have a bunch of these assignments coming in, and if you put on that subject line exactly what it is, at least put your name at a minimum, so that way I know whose it is, because otherwise all I see are numbers, and it's very difficult for me to keep track of it. So when you're uploading something from that cam scanner, make sure that you're in batch mode. And when you're doing these assignments, as I started to grade these, please, I beg of you, write big and write dark and write clearly. So otherwise, it's very, very difficult for me to sit there and try and look at these on an iPad and see exactly what you have going on. So that's the assignment, or that's the lecture. I'm going to scan this assignment and send it to you so that you can figure out, make sure that you can do this. No, you do not have to send this to me. The only thing I want to do this week is going to be those 2 problem assignments. And don't forget, we're going to have the online meeting tomorrow at 11 o'clock. And so I will see you all then. Take care.